and welcome to Disseminate, the Computer Science Research Podcast. I'm your host, Jack Wardby. Today we have another installment from OSDI 2022, and I'm delighted to say I'm joined by Konstantinos Kallas, who will be talking about his paper, Practically Correct Just-in-Time Shell Script Parallelization. Konstantinos is a PhD student at the University of Pennsylvania, and he is on the Technical Steering Committee of PaSH, which we'll be learning more about today. And his research interests lie in the intersection of programming languages, distributed systems, and software verification. Konstantinos, welcome to the show.
Hi, Jack. I'm glad to be here. Yeah,
It's great to have you. So let's dive straight in. So, can you tell us a little bit more about yourself and maybe how you became interested at researching at the intersection of these three areas?
right. So, I guess my background, or at least in my undergraduate, I worked a lot on compilers, and I particularly worked on a compiler for the language Erlang. My advisor at the time was one of the Konstantinos Kallas, was one of the developers of the ahead of time compiler for Erlang, and I worked on a just-in-time compiler for it. Erlang really instilled in me like some interest and love for distributed systems because of how nice and clean it makes it to develop such systems. And then during my PhD, I slightly moved towards verification and more theoretical programming languages. But I'm now coming back home to the systems side, and I think that's where I probably lie, like in the system side, but with programming language perspective and principles guiding what I'm doing. Yeah.
No, that's really nice. Yeah, you can kind of see you kind of come full circle almost there. Yeah, that's nice. So the paper, the start of the show today is all about the shell script compiler PaSH-JIT. So maybe you can give us an elevator pitch for this work. And also, obviously, this is part of a larger part of work as well. So maybe you can give us an intro to the whole project as well.
That's right. Yeah, I guess I would probably give you an elevator pitch of the whole work, because this paper is only part of this whole PaSH parallelizing compiler for the shell. So I guess the pitch is that shell scripts are ubiquitous. I guess everyone knows that already. Something that I did find very interesting recently that I saw is that on the GitHub yearly survey, the shell is the 8th most popular language across GitHub. That just shows, and it's been consistently on the top 10 for many years now, and I guess since its inception, I guess. But so it's extremely ubiquitous, but there is no actual. Most scripts are sequential by default. You get this pipeline parallelism by writing pipelines, but that's it. And essentially, what we do is provide parallelization for the shell. But this was hard to do before, and this is because of the main three challenges, we think at least, of the shell, and three of its characteristics that make it very hard to develop principled solutions on top of it. So these three issues are first of all, shell scripts allow for shell programs and shell scripts compose arbitrary black box commands like grep, sort, arbitrary commands. And all of these are written in different languages. Essentially, what you have in your system is just a binary of the command, often. And that means it's extremely hard to make any form of static analysis on these commands and then lift these results of this analysis to your whole script. So that's one very, very hard problem that makes the shell extremely hard to deal with and develop tools for. Another thing is that its semantics is extremely complex. The POSIX specification, the POSIX shell specification, is I think multiple hundred, many hundred pages of English that is also underspecified in many places and so on. So in the end, what we end up with is like more than 20, I think. I think that's a low estimate of shell implementation. Exactly. That's right. So we end up with like many, a lot of shell implementations, and none of them can be, all of them diverge in different parts of the spec. And so if one wants to develop some new research and they develop a new shell to carry their research with, like a parallelizing shell, for example, if we develop the parallelizing shell, that would diverge from all other shells too. making it extremely hard for someone to actually use it, because then they would have to break their scripts to adopt our research. And the final thing is that the shell is extremely dynamic as a language. So you have these behaviors like a simple string can contain a command substitution. So the result, the value of a string could depend on the files in your directory, in a specific indeterminate directory in your system. So there is no way you can actually predict or analyze statically a shell script and be able to have any form of precision with this analysis. So these three characteristics of the shell make it extremely hard, in our opinion, to develop any kind of solution on it. And that's what we have essentially covered with our research until now. So with respect to the commands, we came up with a command specification framework that we use to decouple essentially the analysis process and allow for the development of tools that know something about the behaviors of the commands through these specifications. And then it's the job of the command developer or some expert to write the specification for the command and make sure that it's correct with respect to the command implementation. And so this gives us, this solves the first issue, or at least makes a dent towards solving it. Then with respect to the semantics, we built our whole infrastructure as a shell-to-shell transformation. So essentially, we do not re-implement the shell. We just produce a parallel shell script, which we then run with the original interpreter, allowing us to get extremely high compliance with an existing interpreter. In our work, that is PaSH. But yeah, translating the original script to a new, better version of itself and running it on the original interpreter allows us to get very high compliance. And finally, for the dynamic aspect, we developed a just-in-time compilation infrastructure. Essentially, this is not like traditional just-in-time compilers, but it's more like a very tight orchestration framework that integrates with the shell and essentially reads a little bit of the input script and then decides at runtime whether it should give that script to the shell to execute or rather transform it to a better version of itself and then give it to the shell. So this very tight integration and incremental, let's say, execution of the script allows us to get compilation at the right time when all of the dynamic things have been resolved. So when we see a string that contains an ls inside, the command substitution and an ls, we can actually ask the shell, the interpreter, please expand this using the just-in-time infrastructure, and then say, okay, can we now do something about this whole region of the script that we have expanded, and we know what it's supposed to do. I guess that's a very long elevator pitch, but
no, that's great. That's great. So obviously we're gonna focus on the JIT stuff today. But are there any where's a good reference to go and check out the prior work on this? What would you direct the listener to? I'm guessing you've got plenty of papers on this. So what would be the best place to start looking?
I think for the commands and the shell-to-shell compilation infrastructure, the foundation of it, our EUROSYS 2021 paper that's called PaSH Light Touch Data Parallel, I think shell parallelization should shell compilation or something should be a good starting point.
Great stuff. We'll link that in the show notes as well, so the interested listener can go and follow up and look at that. So let's talk more about PaSH-JIT then. So you sort of outlined sort of four main sort of areas, four main features to the compiler. Let's go through them one at a time, and we'll dig into each one. You can tell us what it is, like what it's set there, how it works, and kind of what problem it's solving. So you start one of the sections is about dynamic interposition. So what is this? Why do we need this? And what's the problem it's solving?
That's right. Okay, so the dynamic interposition is essentially the solution that deals with the dynamic issues, and it's this integration part that I talked about in the beginning. So essentially, how we achieve that is that we have a preprocessor of the script that goes and instruments the script at multiple places with calls to our just-in-time compilation engine, let's say. And then at runtime, when this is called, the actual script is called, at various places we enter the JIT engine loop. And that's essentially the integration part that I talked about in the beginning. Yeah.
Okay, cool. So when it goes through and instruments the script, what is it looking for to like instrument? Like what areas are kind of, oh yeah, this we can instrument this. So when it comes to it, we can parallelize this area. What are the sort of hooks you hook into there?
That's a good question. So we find areas where that we call in the paper data flow regions, and these are areas that look like they could benefit from parallelization. And intuitively, what they are is compositions of commands with pipelines and the background operator, the ampersand in the cell. So these are regions of the script that are supposed to execute. They are supposed to execute multiple commands concurrently, and we each of these regions before it, we essentially replace these regions with calls to this just-in-time engine.
Do the annotations always work, or is there a chance where you get some sort of false positive of the annotation, or is it always going to work? Or like, is there? I guess maybe we can touch on that later on when we do the evaluation, maybe, or we talk about that. But is there something where it's not 100% correct all the time?
That's yeah. I mean, it could not be correct. So the preprocessing is essentially just an optimistic path.
Okay, I see. Yeah.
Let's replace all of these things with a call to the just-in-time, and then at runtime, what happens is that we actually go and check whether we know enough things about this region and whether it is actually parallelizable. And sometimes it's likely that it's not the case. If this region contains, for example, an RM command deleting some file, we don't want to touch it. So what we do is fall back at runtime to the original region. So essentially, the preprocessing just needs to be optimistic, and it over approximates the places where we could get parallelization, and just make sure that it covers as many of them. And then at runtime, we make a sound decision of whether we can actually parallelize the region.
Okay, cool, nice. So let's talk a little bit more about the JIT engine then. So obviously, this is a kind of, I guess, is one of the main components of this whole thing. So let's go into that. Can you tell me how that sort of looks and what the structure looks like and how it works?
Right. So I guess the JIT engine is at its core is first of all, it's a shell script. At its core, what it does is that it hides from the perspective of the user and the shell the fact that we are now entering in a compilation investigation mode. So what it does is it saves the state of the shell at that point, and that includes all of the configuration that the user, the ways the user could have configured the shell, like using the -e flag, which exits the shell on an error, or the -v flag, which gives you verbose output. And so saves all that to be able to revert it later, and then sets the shell state to an internal, PaSH internal state that is very hidden in a way. It doesn't expose any information to the shell and the user, and then asks the compiler whether that particular region that was there at the time can be parallelized or not. And the compiler responds something, yes or no, and then the JIT engine restores the state of the shell, the original one, and then executes either the optimized parallel or the original fragment.
Okay, nice. So there's in the case where we can actually we can actually parallelize this. The parallelizing compilation server kicks in here, right? So at this point, how does this work then? So once it works out, yeah, this can be actually optimized. How does it go about doing this?
Right. So that's the part of the compiler. So what the compiler does, it has a whole pipeline of things that it does, and the first thing that it does is it asks the interpreter to expand all of the strings in that region. All of these things that could contain arbitrary command substitutions, whatever. This could be even there could be even a whole command, a whole program inside the strings. And it does that by simply asking them, okay, well, I'm actually lying. So the original implementation was that it was asking the interpreter to do it for it, but that ended up being very slow. So what we ended up doing is re-implementing our own expansion on top of it and covering a big percentage of all the cases, the common and safe expansion cases, and doing that in our internal Python library. But yeah, you can think of it. This should be equivalent to just asking the interpreter to do it for us, the expansion, because essentially at that point we have all the information we need. We can reflect on the file system, execute the command, do whatever we want. So after expanding the strings, we have a fully expanded fragment of the script, which could be a pipeline. Let's say it's a pipeline. And then what PaSH tries to do is for each command in this pipeline, it tries to find the command specification and try to see whether, first of all, whether we have this command specification, because we might not. And if it has it, it tries to transform this command to a data flow node representation. And the commands that we can do that for are the commands that are what we call pure in the paper. And that means that they only interact with their environment by reading from a well-defined set of input files and writing to a well-defined a set of output files. And so that's a command that where we know the inputs and outputs, we can turn it into a data flow node with well-defined inputs and outputs. And then it does this for every command in the script. And if all of them succeed, we have all of these commands that can be composed in a big data flow graph. At any point, by the way, until here, if something fails, if some specification is not found, if something goes wrong, the compiler simply gives up, falls back, and then the original fragment is executed. So all of this process does not need to be complete in a way. It works only if we have the specifications and so on. Yeah. So once we have the data flow graph, this is a very clean abstraction, and we have developed like provably correct transformations on top of this data flow graph that we then apply and transform it to a parallel data flow graph. Essentially, the transformations that we do are all simple divide and conquer parallelism. So if a command processes its different input lines independently, then we can simply parallelize this command and give a subset of the lines to each of the parallel instances, and then concatenate the results. So that's the main idea of how we get parallelization in the data flow graph. And then we simply have a backwards pass that takes the data flow graph and transforms it back to a parallel shell script by instantiating all of these nodes in the parallel data flow graph to back to shell commands.
That's really interesting. So, I mean, in the general case, do you find that I mean, obviously, again, we'll probably touch on this more when we talk about the evaluation. How likely is it that I'm not just going to end up with big one long dependency chain of you've got to do X, Y, and Z? There's no actual opportunity for parallelism there. There's like a dependency chain that you can't move things around. Is it quite unlikely that it happens, or is it pretty common that you can actually do things smarter?
Right. So I think one thing so we do find and discover dependencies too, but I have not talked about this yet. So that's later in the paper. So the parallelization I'm talking about here does not talk about dependencies. Even if you have a single command, let's say you have a sort, right? Somewhere in your script, you call a sort, and it writes to a file, and the next command in the sequence reads from that file. So these are dependent clearly. But even this sort on its own, it can be translated to a data flow graph.
Okay, so we're within one thing. Oh, okay, right now I see.
And split it up into multiple sorts that then merge their output with sort -m. So essentially, for many commands, we have this kind of aggregation that we can do after that, and parallelization. So even at a single command level, and essentially, if you had a sort followed in a pipeline by another command, then we would parallelize the sort and then parallelize the next one, and also make sure that the combinations between all of these parallel instances are efficient in a way. And so we get a pipeline and data parallelism. Yeah.
Fascinating. Yeah. Sorry, I was getting ahead of myself there. Cool.
This is a common, I think, misunderstanding about this work, and I think everyone in the beginning assumes that the main thing we do is figure out these dependencies, but we actually do more, and the original work does this data parallelism.
So I guess where does the commutativity awareness fit into this then? So this is, are we talking here within like an operation, like a sort, or is this again like sort of the level up?
So that's totally right. It's within a command. So
within a command, okay.
Yeah, that's right. So before in our first paper, the PaSH paper, we came up with transformations that do not require commutativity. And these are pretty good. They get you really far. But some commands actually you can do better with commutativity. And these are commands that either process each line of their inputs independently, like grep. For example, with grep, you search for a pattern in each of the lines independently. So as long as you make sure to reorder the lines after the parallel greps correctly, you get the same result. So we call these commands stateless in the paper because they don't require any state across lines. So with stateless commands and commutative commands like sort, because sort, all of its inputs, it doesn't matter the order with which the lines arrive. In the end, the result will be the same. We can actually do better than just the transformation that we had in the original pass. And essentially, doing better means doing a round robin passing of lines, which allows us to have better, finer grained parallelism. Because in the past, in the original pass, we just split the input file in big chunks and then gave each chunk to its parallel version. But that requires running through the file once first, right? So you pay the cost of running once through the file, and then you can split it. But with a round robin, you can pass 10 lines to its parallel instance in a round robin fashion and essentially stream it towards the downstream parallel instances.
So, I mean, I guess kind of how did you go about implementing this then? So was it pretty straightforward? So you said it's obviously it's a shell script itself. Was it a big implementation effort, or was it? Yeah, I guess talk us through how that went.
So the implementation is all of the compilation stuff is in Python, just for simplicity, I guess, and a lot of the glue is in the shell because we need to have this tight integration with the shell to do a lot of things. We cannot avoid it essentially being in the shell for a big part of the time. Yeah, I guess the effort there is not. I guess there's a lot of code in the compiler as a part. And there's not a lot of code in the shell part of the implementation. But coming up with this code was a very, very long process because I think we'll talk about this in the evaluation, I guess, if we go through it. But we made sure that our tool passes the whole POSIX shell test suite, which is more than 29,000 lines of code. And so, this took me about a year of engineering, and figuring out why is this test failing. All of the tests were big, first of all, and it was a very, very, very long process to actually achieve this compliance. But
Cool. I just wanted to ask you a question real quick about when you said that the commutativity awareness in it, like. How did you decide which things commute or not? Was it kind of obvious, or was it like a trial and error sort of process, or did you sit down and sort of like prove that the two things definitely commute?
So we did not prove anything, but we did a thorough, if you can say that, analysis of a lot of commands that we found out there, and just added the commutativity field in their specification. That's what it took to annotate them essentially. And we went through a bunch of commands and did our best to decide if they are commutative or not. And I mean, in our evaluation, we do a lot to check for correctness, and we run on very big inputs, a lot of scripts, and all of them give equivalent outputs to BASH. But of course, that's not a proof. So our hope is actually next. We have some next steps with respect to checking the specification correctness. But
experimentally proven, then, shall we say? Yeah.
Practically correct.
That's correct. There we go. Right. Yeah. That's cool. Great. So let's talk about the evaluation then. So it sounds like it was a very, very extensive evaluation, but let's take it back a step and talk about what questions you were trying to answer and what that sort of experimental setup looked like and what benchmarks you ran in addition to the POSIX test suite.
Right. So I guess we had two main questions that we want to answer. The first is correctness. And I will explain maybe later what exactly that means, because when we talk about correctness, Actually, we can talk about correctness maybe completely first and then go to performance. But the two questions are correctness and performance has sub questions. But with respect to correctness, what we wanted to show and evaluate, I guess, is whether PaSH on top of BaSH. It's very hard to differentiate the two with the sound only, but PaSH with a P, our tool. Whether it has the same exact behavior with BaSH, the shell interpreter, in as many POSIX shell tests as possible. So we don't want to pass all the tests, but we rather want to pass and fail exactly the ones that BaSH does too, because even BaSH doesn't pass all of them.
Okay.
So yeah, out of the 400 tests, I think there are 400 something, all the tests that were applicable in our case. PaSH versus BaSH, they only diverge in two tests, and the divergence is actually not even, it's actually distinguishable, and it's only, so the divergence is that both fail, but the error code of BaSH is 1, and the error code of PaSH is 127.
Okay.
There's a very little it's a very weird the reason why this is happening, but it has to do with the way we are calling BaSH. We have to call it in a particular way using the -c flag to set its name. That's a very, very, very low level detail, but essentially this is what BaSH gives us. This is the error code it gives us, 127, and therefore it diverges with the original way of invoking BaSH, and we haven't found any way to actually resolve this. We have also contacted the BaSH developers, and they do not intend to change that at any point. So we're kind of stuck with this little divergence. But yeah, practically, it's like it's virtually indistinguishable, I guess, from BaSH. Other than that, and I guess we also run on about 80 scripts that are the ones that we used in our performance evaluation too. We run them on multiple gigabytes of input, and all of the output is the same with BaSH. So that's also another boost to our confidence that PaSH is correct.
Yeah, nice. I mean, I'm just kind of looking through in the paper now that the range of where these scripts came from. So there's a wide range of of different sort of domains they come from. Was there any reason why you settled on these specific benchmark sets, or was it a case of these are the ones that kind of everyone uses, or what was the rationale behind it?
Yeah, that's a good question. So there's not a lot of research on the shell, especially performance and the performance of the shell before our work. So in the original paper, we found a lot of pipelines, and that's what we used for our original paper, because we mostly dealt with pipelines at the time, and many of those come from GitHub and other real sources, and they're pipeline scripts that we found essentially in the wild that do some non-negligible data processing. I guess that was the main way of choosing them, because if they don't do any data processing, then we wouldn't be able to parallelize anything and get any. It wouldn't make sense. And I guess the most interesting out of those, I think, the pipeline ones, is the COVID MTS benchmark set. So that one, a professor from a Greek university called Diomidis Pinelis actually wrote his scripts during the pandemic to help a journalist measure whether buses in Athens were actually increased frequencies, whether frequency of the buses were increased, because that's what the Greek government said. So that professor wrote these scripts and actually downloaded a bunch of telemetry data from buses and processed it with his scripts to see if the frequencies of the buses in Athens were increased during COVID, which was what the government claimed.
So the government was claiming that we had more buses because that was, what was the reason for having more buses? Was it
so that people they're less crowded, I guess.
Okay. What was the conclusion?
It turned out not that much. But, Yeah, this script was. I mean, we really we got it. We were very happy when we found it because I mean, we were asking around, do you have shell scripts that do data processing? You know, and this professor came in and we were like, wow, this is amazing. Yeah.
That sounds a great find. Yeah. So let's talk performance then, anyway. So I guess give us some numbers. How well does it perform?
Right. So let's see. Yeah. First of all, yeah, we ran about 80 shell scripts, as I said, and I guess the main conclusion from our performance benchmarks is that the just-in-time version of PaSH is always faster than the ahead-of-time version of PaSH. It's almost always faster than BaSH, the sequential version. And with respect to the ahead-of-time original PaSH, it also extends benefits to many scripts that the original could not handle. So actually, any complex script that contains a complex control flow, like if then else's or for loops or dynamic behavior, without the just-in-time compiler, you cannot handle it because you cannot statically determine what will actually happen and how will these variables and these strings expand at runtime. So I think some numbers are the average speedup of PaSH-JIT on all of those scripts is about 5.86. That's on a 64-core machine that we used, and the PaSH ahead of time is about 2.9. And that was only on the scripts that it could actually handle. We didn't even measure the rest, which doesn't even apply. And the only few scripts where we are slower than the sequential one are ones that perform tiny computation. So there was one script that just essentially keeps the first line of its input, which took 8 milliseconds for PaSH to execute it. But for PaSH-JIT, it took about 1 second because of all the initialization that we need to do, and so on. So this is, I think, the only scripts that we were slower than the sequential are ones that do negligible computation, and so we pay the constant overheads up front, and that's where the slowdown comes from. Yeah.
Sure, yeah, because I was kind of going to ask, like, leading into the next question of kind of what the limitations are when situations when like performance is suboptimal.
Right.
But like, kind of, what are the characteristics of the scripts where I mean, other than it being like a really tiny computation, are there any other characteristics that would maybe mean that BaSH would be the right option to go with? Or yeah.
Right. I think that if you have any script that has tiny computation or very tight loops with not a lot of computation, so that would take there you would get a benefit you wouldn't get a lot of benefits by using PaSH. I guess also if you do not have any specification for any command in your script, then PaSH-JIT also cannot do anything for it. So yeah, I guess a main assumption behind all of this work is that you have some specifications for a few commands in your script, or you use some standard commands. We have written about, I think, more than 70, something in that range, 70, 80 specifications for commands. And we cover a big bunch of the standard ones, but if you use some completely third-party custom command and you don't have the specification, PaSH is gonna just
yeah, you're on your own there, right? Yeah.
Yeah, exactly.
Cool. So continue. Continue.
We did a little. We really tried to reduce, I guess, the overhead of our JIT engine and this in and out essentially calls between the JIT engine. And we have also a small part in the evaluation of the paper that we show that. And the best we could get in the end is, I think, about 50 milliseconds per entrance to the just-in-time engine. So that's the lowest we can get. In the end, we were happy with this, but I think that's one place where one could potentially seek for an improvement to make this tool actually having no negative impact if you ever want to use it. Yeah, because I guess there is no trade-off that would need to be done there to achieve very low latency, which is that you would probably need to integrate into an original interpreter, so modify BaSH itself to the just-in-time engine. So because we wanted to avoid that and essentially have this loose coupling with an existing interpreter, we ended up with and having this shell-to-shell compiler infrastructure. We ended up that's the lowest we could get with respect to latency.
Yeah, in that sort of setup, there's always going to be some of it. You're never going to truly get rid of it all, right? So, but I mean, yeah. But so, I mean, obviously, in the experiments you compared against PaSH, and obviously, kind of the ahead of time version of PaSH. But like, what you mentioned, there's not really much other work in this area. What is the nearest sort of, for lack of a better thing, a competitor other than PaSH sort of thing? Is there any other sort of research?
So I think there are a lot of recently I have been seeing more and more interesting research in this topic. So I guess there are three papers by three different groups that I've seen out there that look really promising. They're not exactly doing the same thing as what we do, but they're in a similar space of shell research with respect to performance. So one of them is a paper that was actually published at using XNTC this summer. It got the Best Paper Award also. It's called Riker, Riker, and what they do is they essentially get automatic incremental execution for a shell script, and they do it by tracing. So essentially, what you do is you write a build script, your build script, for example, using just a shell script, not a make-file. But then when you run it, it automatically finds all of the dependencies between the different build commands. And then the next time you run it, it only runs what actually changed, what actually needs to be rerun. So it essentially creates the make-file in a fine-grained way automatically by tracing the execution of your script. Yeah,
that sounds interesting. Is that? I mean, we're kind of diverging a little bit here, I guess, but like, does that probably perform better for different types of computation, though, that you want to do, or is it?
I guess Riker is mostly targeting build scripts and where you have a lot of dependencies between commands. Your commands usually in build scripts, they don't process their input like in data processing where they read their input line by line, but they read the whole source file, for example, and then they do something with it. It's more targeted towards this let's say build. I think I would call this input-output computations, where you have a dependency graph So that's one work that I found that is extremely interesting. I mean, their work is very dynamic in the sense that there is no concept of specifications, so they discover everything at runtime, and so we're actually interested in investigating the synergy of Riker with our tool. So if we can actually discover some of the specifications by tracing, that's the idea.
Yes, I guess my next question is, I'm guessing this work's publicly available, right?
It's on GitHub, yes. It's under the bin PaSH. That's the organization name, BINPASH.
Cool. We can link that. Also, have you found that it's had quite a substantial impact? You found a lot of people using it, and have you got feedback from people using it?
So actually, we have found that when we published the paper, we saw that some people tried to use it in some of their big build scripts, though. PaSH is not that great with build scripts. So someone tried to run it on the GNU lib build script, which is like a few thousand lines of code. And of course, PaSH broke in the beginning. But then we fixed these errors and we ran the script, and it didn't get benefits because it was highly dependent. It was more on this build script area. But yeah, we saw that people are forking their repository. We hope that someone uses it out there. We are actually trying to also keep an eye out on people that could potentially use it. And I mean, our hope is we keep putting resources in it, and hopefully we will get, if we keep persisting, someone might use it at some point. But it's one of our hopes to keep it alive and make sure that we can help anyone that wants to use it at some point.
Yeah, that's great. Yeah, I think with these sort of things, you've got to just kind of stay in the game, right? Be consistent with it and keep it out there, keep spreading it, kind of publicize it, and hopefully, it kind of takes off. How easy would it be then? So for me to say tomorrow to switch it out or to start using it in my day-to-day sort of workflow, what's the usability aspect like of it?
I mean, you could, I think, just if you're using Bash, because that's where we have that's where we can plug in now. I mean, we have not tried to run it with Zis, for example, or any other shell. But if you're using Bash and you're running your scripts with Bash, you can just directly run your scripts with Bash just by downloading and installing Bash, and it should just run. That's the theory. Yeah. I mean, if you find the bug, if you do it and you find the bug, please send it to us. But
yeah, raise a GitHub issue if we find a bug. Yeah.
Yeah. But that's like how easy it should be. So you just download it and run your script with Bash, and then it will do this compilation, run it with Bash as the underlying interpreter. So yeah, and there you would get equivalence with what Bash would give you based on the validation and so on. Yeah.
Nice. So I guess the next kind of few sets of questions are kind of my sort of like stock questions in a way, and I like to see how people's answers to them diverge. So first one is sort of, what's the most sort of interesting and maybe unexpected lesson that you have learned while working on PaSH, and maybe specifically on the JIT stuff?
Right. So yeah, I think that the most interesting, at least, idea that crystallized in my mind while working on this is that if we don't have this loose coupling, as in having a shell-to-shell compiler, and instead, if we implement a shell, there's no way for anyone to adopt this. So I think that's what really crystallized in my mind while working on this. That I spent 1 year to achieve compliance with Bash, and still we are delegating all of the execution on Bash. So I cannot even imagine how much time it would take for someone to try to achieve compliance with an existing shell by re-implementing it. That would probably be a multi-year effort. And so I think the main idea and the most interesting lesson learned, I guess, is that researching the shell for it to be easily adoptable and easy to, and not have a huge barrier for someone to do it. I think everyone should aim for some loose coupling and some form of shell-to-shell compilation or something in that sense, so that they can just plug in existing shells and run with them instead of trying to compete with them. And I think that's the biggest lesson that I learned.
Yeah, it's a really interesting lesson. So kind of, I guess, a question that kind of falls out of that is when was the last time someone sort of tried to compete with an existing shell? Like, I mean, how often obviously there's loads, right? There's like you said earlier on, there's well over 20, right? So how frequently are new ones sort of cropping up where people are thinking, oh, I can do the full thing better?
I think it's very common. And I still even now see on GitHub often like, you might like this repo, and it's a new shell. And they all do their own little tricks, their own little interesting features, like some of them handle arrays, some of them have objects. Each shell does something better, but it feels extremely hard to migrate all of your existing shell scripts to your new shell. So that's, I think, a very, very big challenge. It's impossible to migrate all of these legacy scripts that we have to a new shell if we don't have compliance. So it's very easy to make a better shell, but then how do you switch to it? There's no plan, I guess. Or it takes many, many, many years. So in the case of Zis, for example, it now, I think, it probably, if I'm not mistaken, it became the default shell in Apple computers, Zis. But that took, I think it has been in existence for, I don't know, like 10 years now, right, maybe even more, and being heavily engineered continuously, and pushing for its adoption. And it has now, like, it's not even that everyone has switched from Bash to Zis, but okay, Apple computers run Zis, but that took so much time and so much energy. So yeah. It's
funny, like even with databases, right? Like people constantly, but they think, I can do it better. I'm going to build my own database, right? Like, it's just like everyone thinks they can do it better, right? In a long weekend normally as well. Give me a long weekend, I can create anything. Yeah.
That's like the XKCD comic, That's all the standards are wrong.
Exactly. Cool. So I guess let's talk kind of the journey and sort of any sort of war stories you kind of had along the way. So this is a kind of quite a sizable implementation of, or kind of trying to get compliance, right? Was a bit of a battle, it sounded like. So kind of from the initial idea of for PaSH to now, to the OSDI publication, what were the things that you tried along the way that failed? And yeah, give us the sort of the war stories and talk about that journey from start to finish.
Right. Yeah. So I guess this started like it was in the summer of 2019. That was when we first considered
pre-COVID. Then,
yeah. It was a very long time ago. Yeah. And actually, yeah, it was one of the collaborators in this work, Nikos Vasilakis, who's now a professor at Brown. He was then a postdoc at Penn or transitioning to MIT as a postdoc, I think. He called me and he told me, I've got this crazy idea. Let's distribute shell scripts. And I was like, this is a super dumb idea. Like, it will never work. Why are you calling me? It was like late in the evening or something. And yeah, and I was like, this is completely ridiculous. Like, it's never going to work. And then, yeah, somehow he convinced me that we should try it out at least. And yeah, we in the beginning we were like thinking that we would distribute shell scripts. So that was the idea. But actually, the first iteration of the first PaSH paper, we said it's a distribution engine for shell scripts, and it got massacred at some. I don't remember, it was PLDI 2019, I think, or 2020, and I think it got like extremely like terrible reviews. Like, this paper is terrible. Yeah, and then we were like, okay, distribution is hard. Let's just do parallelization for now.
Yeah.
And that's how we lowered our expectations. And then I think we submitted this paper at OSDI 2021 and or 2020, I don't remember. And there we had the most surreal experience because there were 6 reviews and 4 of them were accepts or strong accepts. So like
Wow.
not weak accepts or strong accepts, like the ones that say, I will champion this paper. And the other 2 reviews were like rejects, like not weak, rejects. And so there was a very huge dissonance from the reviewers' perspective. And 2 of them said, this is complete garbage. We should not publish this garbage research. And the 4 others were, it's good. And then it didn't get in. And we were like super furious because, and eventually it got in Ulysses, where it also got the best paper award, which was actually funny because how it turned out. But yeah, after that, this work has been going very smoothly, I think. But after this first 1.5 year of real hard, pushing for it and so on.
Yeah, like 18 months of grind, but like worth it in the end, I guess.
Yeah.
Cool. So I guess what's next then? So where do you take it from here then? So what else is in the pipeline? Are you going to go down the distribution route now, distributed version, or is it...
That's a good question. Yeah. So we actually, we have a conditionally accepted distributed PaSH at NSDI 2023.
Congratulations.
Yeah. It's conditionally accepted yet, so we have the confirmation. But after 4 years, I guess it will be the distributed version will be published. Somewhere. So that's that. But then we have a ton of ideas actually, and I mean, I think there is a lot of interesting synergy that could be investigated with dynamic approaches like Riker. There's a lot of work to do on parallelization optimality, because currently we just showed that we can do parallelization in the shell, but we haven't thought at all about how to do it well. Like, we just parallelize, okay. But how much, there are a lot of parameters that can be tuned, heuristics that can be improved. So these are like some directions. And I think for me, the biggest direction, I think the biggest problem that exists at the moment with the shell is correctness and maintainability. So we have all of these legacy scripts out there, and like the state of the art, I think I don't think people even test these scripts. It's more like they run. They run in our workflow. So let's not mess with them because they're like these very complex, things. And I think that's where I see the most interesting, and more maybe moonshotty research on the shell where it could happen. It would be great to see frameworks and tools and affordances for developers that would help them make scripts, check that their scripts are correct, or maybe hold their hand while implementing a script, not letting them do any kind of big goof, because you can very easily in the shell like delete your home directory and then lose your computer or something. So yeah, like some hand holding, security hand holding, correctness hand holding, and maybe even maintainability in the sense of porting old legacy scripts to saner languages or saner like coding practices or conventions. So this is where I see the future of our research, and I think that we have done all of these infrastructures we have done now, I guess, and addressing these challenges that I talked to you about in the beginning, the cell challenges and the cell characteristics. I think is a vehicle where one could build very easily other things on top of it. So the just-in-time framework, the cell-to-shell compilation pipeline, and the command specifications, all those three combined could I think very easily at least lower the effort needed to do some research on the cell and solve some other challenges that it has. Yeah.
There's plenty of very interesting directions there. I'm sure that'll keep you busy for a long time.
yeah, hopefully. Yeah.
So, I mean, other than receiving calls late in the evening and with crazy ideas, how else do you like go about sort of idea generation and sort of selecting what things to work on? Like, what's your process there?
I think I'm not that good at it, to be honest, selecting ideas. So I think usually people that I collaborate with come up with the good ideas. I feel that the way I pick, I guess, what to work on is I want to have both know that it's potentially impactful, highly impactful, and understand that the problem is actually relevant. And that there is a clear application that people are actually doing at the moment. So that's one big benefit of this shell research, that I know that people are writing shell scripts. It's like this is not So I think I really like problems where and research directions where the impact is clear and practical impact is clear and visible. So I don't like working on some theoretical thing that maybe in 10 years someone will figure out how to apply. I want the research to be actually applicable. And I guess the other thing, which is more the PL programming languages, like flavor to things, is I really try to find like cute and elegant subsets of the problems that can be described in a cute and clean model, potentially also proving that some things are correct in this cute model. So I guess the things that I like working on are this combination of potentially practically impactful and cute, elegant with respect to the models and representations. Yeah.
I guess kind of my kind of next question I kind of want to ask you is, I mean, maybe I kind of know the answers already, kind of given what we spoke about today, but what do you think sort of the biggest challenge in with like shell scripts and with shells in at the moment? Like, I mean, maybe something like the fact that like migrating from one to the other is pretty like challenging. I guess that feels to me like it'd be a big sort of one of the big challenges. But what do you think is the sort of biggest challenge out there at the moment?
Yeah, I think that's right. Porting, maintaining, and checking the correctness of shell scripts is like we are lagging. Shell scripts are lagging behind other languages with respect to what affordances they have on all those topics. Like for decades, they are lagging behind decades. So I think that's what we would like to push, and what I think is a very relevant research focus to try to bring a lot of the knowledge and affordances that we have in other languages to the shell, and actually make them more testable, maintainable, better, make it easier to reason about what they will do, what their correctness is, and so on. Yeah.
Why do you think it is that it's kind of almost been just left? No one's kind of tackled that problem like, compared to other programming languages. Why do you think it's been left to get to like the state? It's because everyone uses these things every day, right? Like it feels strange that such a fundamental sort of thing has kind of been left in that sort of state.
That's true, and we were also not sure about that. And our hypothesis is that because of these challenges that it has, its characteristics, which make it great, also these characteristics, right? Because the fact that you can compose black box commands allows you to do very, very succinct, powerful scripts. But it's also this problem that you don't know what these commands are. So then how can you develop a principal solution that deals with many of them and that's generalizable? The fact that it's very dynamic, it's great because you can introspect and reflect on the state of your file system while you're executing your script. So a for loop, its iterations could depend on what files you have in a specific directory, for example. And that's very powerful to use as a developer. But then also, if you are like a programming language, a framework designer, or like a systems researcher, you cannot write an analysis for the shell because it's so dynamic. It's like just impossible. So we think that these characteristics, that make the shell great, also make it very hard to actually tackle and do principled search for principled solutions in this space. And this is our hypothesis, of course, and it's we're a little bit biased. But that's what we think was the biggest roadblock. So yeah, our hope is that we're making a small dents on all these problems, and ideally, by building on top of this, we can bring ideas from other languages. We can make the shell a little bit saner.
Yeah.
as a setting, and language. Yeah.
So yeah, that's interesting. Yeah. So I guess it's time for the last word now. So what's the one key thing you want the listeners to take away from your work on PaSH?
Yeah, I guess research on the shell is possible again, we think. Do more of it. Yeah, you should all do research on the shell, and if you
call to arms.
Yeah, exactly. Yeah, call to arms. Exactly. Yeah, and there's also other work, not just by us. Like this Riker paper, for example. There's an offloading shell. It's called PaSH by a group at Berkeley and Stanford. I think that came out a few years ago. I think we should do research on the shell. I think it's possible again that people should consider it again as a relevant place to do research. And I guess something more specific is that download PaSH. It's very easy. It's compliant, you will not break your scripts, and you might get parallelization. Yeah.
Brilliant. Well, it's a good message to end things on. So yeah, thank you so much, Konstantinos. If the listeners interested in knowing more about your work, then we'll put obviously all the links to everything in the show notes, and we will see you all next time for some more awesome computer science research.